Just to resume the lecture where I left it last time, I left you with this call to action that we should study higher geometry of gerbs, and this resulted from my analysis of the question of how to couple higher messenger fields, starting with the 3 form instead of the Maxwell 2 form, to currents of extended charge distributions. And for the sake of this argument, this can be relaxed. It actually will be relaxed in what follows. I further assume that the charge distribution has the topology of the circle. So we're talking about charge loops. All right? And I gave you the, in order to kind of tailor a higher geometry of the gerb, I started with the cohomological, hypercohomological description in parallel with the same development for the Maxwell field, which is perfectly understandable because it exists for a closed 3 form. I just have to choose judiciously the cover of the support of the 3 form, of this closed 3 form. And then on elements of this open cover that are contractible, I have locally smooth 2 forms and so on and so forth. There's this hypercohomological ladder of objects. And I have also actually put them to some good use already, because I have constructed this surface holonomy guy. In other words, the topological term in the Dirac-Feynman amplitude for the charge loop current in an external 3-form field. And now I'd like to, since this is about the higher geometry of the higher gauge theory, so let me provide you in a hands-on way with this higher geometry, so that you see the difference between a bundle, which we arrived at in similar circumstances, when talking about the geometrization of the 2 form with integer periods, and whatever comes now, which is the geometrization of a 3 form with integer periods, which then, if you insist very much, is the thing to consider when you have strings propagating in an external background, that of faraway strings sort of vibrating in the gravity mode and faraway strings vibrating in the Calvert-Ramond mode. If you want the string theory parlance, although I don't need it here. Okay. So this looks preposterous, but it's also elementary. So let me walk you through it. How do we... Oh, it also looks funny, which is good, right? Keeping the spirits up. So, all right, so we start with this manifold of which we have a 3 form, and it is closed, and it has integer periods. And now I have this bunch of locally smooth 2 forms, locally smooth 1 forms on overlaps of the domains of the two forms, and then functions on triple overlap. I will solve a higher geometry out of that, keeping track of the basic features and not the details, which I will then abstract into a definition of a bundle gerb, which will be a geometrization of the 3 form. It will not look so preposterously complex, but it will have all those properties, and then this will be a model, a working model. So a proof of existence of such a thing associated with a 3 form with integer periods. So you see, if I have a bunch of 2 forms which only exist locally on X, on the OIs, I can, in a sort of cheap way, provide you with a manifold which surjectively submerses X, namely take the disjoint union of the OIs on which the 2 forms exist, and equip it with the standard disjoint union topology and smooth structure. So it's cheap because what it says is that this 2 form is smooth if any of the BI is smooth on the corresponding OI. Well, that's cheap, but let's move on. Then I would take actually what I'm getting here is, so technically I would just take the disjoint union of the double intersections, but this is technical. Let us instead look at it conceptually. This is an X-fibered cross product of 2 of these smooth spaces. If I take a fibered product over X of the disjoint union of opens, I get the disjoint union of intersections. That will play a role later on when I sort of conceptualize this construction. And again, cheap trick, on these I put AIJs, and this is a smooth one form. But then I do more, one thing more, in order to get access. So these AIJs are just, if I pull back this two form, cheaply smooth on this surjective submersion over X, if I pull it back by the two projections, canonical projections from OIJ, just to make it clear what I'm having here, is I have, what is the point here? It's X, which sits in OIJ, and there's an index I, and there's an index J, which tells us where the point came from. What are the two projections? It's Xi, projection 1, and it's Xj, projection 2. All right, so these are the projections. If I pull back this guy, the two form, cheaply smooth, by the two projections, and compare the two objects, then this is supposed to be D of this A, cheaply smooth upstairs. So I'm reconstructing the lean cohomological relations that exist between the BIs, the AIJs, and so on. And now, in order to reconstruct the relation between the AIJs, like this relation, AJK minus AIK plus AIJ, readily understood in terms of Czech cohomology, on OIJK, that is here, is the logarithmic derivative of GIJK, I have to do the following. And let me do that. I have to do the following. I have to construct a line bundle, a trivial line bundle, with connection over this manifold, the X-fibered product of two of these surjective submersions over X, and equip it with a principal connection. CX principal connection. And as it happens, if I now form the triple X-fibered product of the surjective submersion with itself, on it I can encode the GIJKs and the cohomological relation between these and the AIJs by insisting on the existence of a distinguished principal CX bundle isomorphism, connection preserving, between the pullbacks of this guy L, suitably tensored here. So this is like, if you look at it closely, it's basically a binary operation on fibers of the bundle L over the same point in X. Okay, good. So so then I have to still impose the cocycle condition on the GIJKs, and this I do by looking at the various pullbacks by canonical projections of this distinguished bundle isomorphism over the disjoint union of OIJKs. And actually, this has a nice interpretation that the way I impose the cocycle condition for the GIJKs reads as the associativity condition for this binary operation on the fibers of L over X. So I have a groupoid structure on fibers of bundle L. And now I abstract from it the definition of the bundle jerk, which, since it will be built, importantly, always on surjective submersions, these have local sections, and bundles, these on contractible domains, are trivializable, I will always reproduce the above picture if I go to the local local trivializations of the objects involved, to local trivializations of the surjective submersions used. So here is the bundle jerk for you. A geometrization of a class in third Durand cohomology with values in 2 pi z, an integral class. So I start with X on which there lives the class, a representative of which is H. Then I erect a surjective submersion over X on which there is a global primitive for the pullback in the Durand cohomology of the pullback of H. Here it was just those BIs, cheaply smooth. But here I construct any surjective submersion with the property that if you pull back H along the surjective submersion, it trivializes in the Durand cohomology, which it generically doesn't do on X. And then there is a 2 form, which is the primitive of H. Then I take the X-fibered, I told you that, X-fibered square of the surjective submersion, And on it, I erect a bundle, a principal CX bundle with connection, whose curvature is fixed, as before, is fixed by the two pullbacks of the beams. And then I take, well, strictly speaking, I take the nerve of the x-fibered pair groupoid of yx, but in human language, I just take consecutive Cartesian powers fibered over x of the surjective submersion, and then I compare the bundles as before, and I impose the associativity condition higher up as a coherence condition. So mind you, a bundle jerk is a 3-form, a 2-form on a surjective submersion, a bundle, hence one degree lower in this hierarchy of objects, where I have functions, bundles, gerbs, then 2 gerbs, and so on and so forth. If you look at the Lie hypercohomology, that's how it kind of combines. You have this ladder of structures, where you have a gerb, which is what it is, then you have morphisms between gerbs, which are described by bundles, and then bundles are themselves related by morphisms, which are functions. And you can go on. And when Murray, together with his student Stevenson, understood the progression from bundles to gerbs, this was like a major jump. Because if you just look at bundles, you have no idea how to continue this hierarchy of higher geometric objects. But once you have understood the passage from bundles to gerbs, there you go. The highway is open for you. All right? And then you have 2 gerbs for Chern-Simons theories, or BF theories, and whatnot. So here's the gerb for you, geometric object associated with an integrable class in H3. And in particular, I have an example of a gerb for you, which is the trivial gerb. What is a trivial gerb? It's trivial in cohomology, so I have a primitive for the 3-form on X. So as the surjective submersion, I take X with the identity onto X, the B on it, the trivial bundle over X times X fibered over X, which is just X, okay? With the sort of 0 connection on the base, and the trivial gluing, like identity gluing. Okay, good. So then I have to geometrize equivalences, but in this geometric, I have to geometrize cohomological equivalences between Bailyns and Deligne 2 cocycles, which themselves describe gerbs, and which I have just geometrized. So let me not walk you through it, but just let me give you the idea. The idea is this, and we have seen it when we were constructing like this bundle L over the fibered product of surjective submersions on which the gerb would trivialize, so would give us the B. Okay? So how do we proceed? The idea, and this is really a paradigm shift in higher geometry, we do not compare objects, the surjective submersions as they stand, but we pull them back to a product, fibered over the base, common base of the 2 surjective submersions, pull back the objects that exist on the surjective submersion, and demand the existence of a morphism up there. This has important physical consequences. This is the idea behind T-duality, for example. You pull back to the correspondence space to compare the 2 dual toroidal vibrations on which string theory lives. Okay? I won't go into the details of this particular construction. This is quite essential. So there you go. Why don't we just compare surjective submersions? Well, where did they come from? They came from disjoint unions of opens on which the 3-form trivialized. But I could refine the open. I would get a new disjoint union, and so a new surjective submersion. It would be the same 3-form, therefore necessarily the same gerb, but I would have 2 different surjective submersions to start with. It makes sense to impose this very strong condition that the 2 surjective submersions just agree on the nose. But if I take the common refinement in terms of open covers, that is, if I take their fibered product over the common base, there, and this is the idea behind morphisms, and the rest is just adjusting everything in higher geometry so as to really realize the cohomological construction. But this is technical, the idea is important. We have the surjective submersions everywhere in the game. We take their fibered products, fibered over the common base, and there we compare. Using a lower higher geometric structure. So if we're comparing gerbs, we compare the gerbs by line, by bundle. If we compare bundles, we compare it with a bundle morphism, and so on and so forth. Okay, so here I basically have the two surjective submersions for the two gerbs whose the isomorphism between which I want to describe. So I take the surjective submersion over the two, and over there I request the existence of a bundle, which then satisfies a bunch of technical conditions which geometrize the cohomological relations between the two Beilinson-Deligne two cocycles. Namely that the two Beilinson-Deligne two cocycles are cohomologous, because that's what I base my geometric construction on. Equivalences in Beilinson-Deligne cohomology. And then there is a notion of a two isomorphism, which I can also geometrize. Let me not spend time here. I can compose one isomorphism. I can compose two isomorphisms in two ways, so horizontally and vertically. And in this way, I reconstruct this geometric weak two category of bundle gerbs with connection. There are a bunch of diagrams which you can draw and be satisfied with it. What I need you to know is that on this two category, we can do pullback. So we can pull back gerbs just as we pull back bundles. And we can take tensor product of gerbs, just as we can take tensor product of vector bundles and of principal bundles with abelian groups. Mind you, these bundle gerbs always have the structure group wherever it appears in the bundles somewhere up there, U1, which is essential to have this tensor product. Without the tensor product, principal bundles have problems tensoring, really. I mean, you can still take the associated construction, but that's a different story. So anyway, the important thing to note is that there is tensoring of gerbs, which on the two cocycles just meant that we would take representative and add them. And there is the pullback. Okay, good. So yeah. All right, so now we're ready to unleash this best theory of the two category for the gerbs to define charge loop mechanics in the presence of defects. I told you that the way in which morphisms between electromagnetic bundles entered the picture in this motivating point-like charge discussion was when we started to consider discontinuous field configuration, discontinuous embeddings of the loop, the Aharonov-Bohm loop, into the target space. Well, likewise here, I could start asking questions: how do I model strings on an orbifold? I would model them on the total space before orbifolding and just allow twisted states, whether these field discontinuities would be controlled by the action of the group that I'm modeling out when passing to the orbifold. So there is enough intuition to motivate the construction of charge loop dynamics with defects, and now let me do just that. Construct charge loop dynamics of the sigma model type, that is the type I'm discussing all along, for embeddings with defects. So what I have to do, technically speaking, is I have the sigma model defined in terms of the metric term, which is completely unproblematic because it's sensorial, and the whole surface holonomy term. And now what I'm telling you is that I have to cut the surface holonomy open at first, say, circular defects, and somehow glue the pieces back together using some higher geometric structure into existing over another manifold into which I will embed the defect circle. Just as previously, I had segments of the circle on which smooth field configurations existed, and I was cutting the line holonomy open and gluing the pieces together using electromagnetic bundle isomorphism. Okay, so here's the picture for you. So imagine a cylinder, piece of the worldsheet, and there we have two phases, to the right of the defect, to the left of the defect, at least the way I see it. And now each of the phases is defined by embedding the half cylinder into some manifold X, on which there is a metric, on which there is a germ, here and there. It could well be that these are disjoint pieces of a manifold, or even worse or better, definitely more elastic in model building. This could be one manifold of some dimension, and this could be another manifold of some dimension. This could be a toroidal vibration for one string background, and this could be the T-dual toroidal vibration. Or this could be one Calabi-Yau, and this could be another Calabi-Yau, and there would be a local T-duality by the wise T-duality. And I could still make sense of string theory on this now glued worldsheet glued out of two pieces, each of which is embedded in a separate sector of the target space. So now, just recalling what I did for the point-like particle, I embed the defect line into another manifold on which it sits squarely here, and this another manifold has to come with two maps to the target space for the phases. Why so? Again, just to remind you, I have two limiting field configurations for the two phases, and it should be arranged such that if I put the defect line in this new manifold and then compose it with the two maps, I should reconstruct the two limiting field configurations for the two phases. And then we sat down on the subject. Well, first actually it was Fuchs, Schweigert, and Waldorf. We did it more generally for intersecting defect junctions, and we actually derived the structure here. So we asked the question with Ingo Hunkel, what structure should you pull back to the defect line to glue the two pieces of surface holonomy cut open in this way together, such that the resulting Dirac-Feynman amplitude does not depend on the arbitrary choices made, like the representative of the Beilinson-Deligne hypercohomology class for the gerb to the left, for the gerb to the right, and so on and so forth. And the answer was this: on this new manifold into which you embed the defect line, you request the existence of a very particular, structurally, gerb-1 isomorphism, which compares the gerb pulled back from the left to the gerb pulled back from the right, and says they should be isomorphic, but not necessarily on the nose. And actually, this not on the nose, this is a trivial gerb, which is just a two-form, a global two-form on Q, and this two-form will be an obstruction. Actually, it will set the kinetic momentum transfer at the defect, and it will obstruct the defect from being topological, and hence the whole thing from being actually a valuable description of a symmetry, which is what I'll come to next. Okay, so you see, by constructing the higher geometry behind the defect in this way, it's not just that you do something fancy, but you actually do something useful. And in the context of Wessel-Minowitten theory, which is charged loop dynamics in compact group manifolds and their homogeneous spaces, this has proven to be enormously robust as a method of classifying defects, classifying boundary states, so like Ishibashi states, and so on and so forth. So this is actually how? Through cohomology. So you know that if you fix the background, the phase background, and if you fix the curvature omega of this defect, then you still get at your disposal a variety of inequivalent models with the defect, which is classified by a certain cohomology group. And sometimes these cohomology groups vanish, and you know that you only have one model like that. This sometimes happens. And sometimes you have the whole variety. If say the defect is the gauge symmetry defect, and you know that there is only one equivalence class of gauge symmetry defects, you know that there is just one prescription for gauging. That's a potent method, and you're doing cohomology, so it's tractable. It's not real numbers, typically it's integer numbers, right? And then, more than that, I haven't emphasized it in the point-like particle case, but you cannot forever do Aharonov form effect. I mean, crying out loud, ultimately you want to compute the model for an open trajectory. You cannot keep talking about coordinate trajectories and diffraction images and so on and whatnot. You want an open trajectory. But the logic of my presentation was this: try to understand the structure that you can put on the Aharonov bond topology of coordinate trajectories, currents, and then go back, cut it open, and ask the question under what conditions, or rather, what should I put at the endpoints? What forces, in other words, should hold an open trajectory? And now I have an answer, cosmological one, a geometric one, because I can actually think of it as a defect. A defect which to the left of it has my field theory, and to the right of it has an empty field theory. How do I realize that? I embedded the rest of the pretzel to the right of the defect. I embed it in the singleton, in a point. Therefore, there are no degrees of freedom there. The jerk will be trivial there. What else? The metric will be trivial there. There's a canonical choice of the metric, the only one. There's a canonical choice of the jerk, the only one. The no jerk. But then I realize that my previous result is telling me that Q now should be a submanifold in X, which I embed the boundary circle, and such that the jerk trivializes on the submanifold. So this puts severe constraints on the choice of what string theories call D-branes. Actually, you can classify D-branes cohomologically. And for the Bernoulli model, it matches perfectly with sort of terribly refined, very rigorous and sort of elaborate methods of finding consistent Ishibashi states. So, and you're still not quantizing anything, you're just doing all good differential geometry, just high. Okay, and then of course you have the homological means of classifying boundary states and defects and so on. And now I want to play a little bit with this notion of this correspondence between defects and symmetries. So first, the naive picture. Let me draw a defect. So here's, to the left of the defect, you have the phase. To the right of the defect, you have a phase. But think of the limiting field configurations in the two phases here. What are they? It's a loop to the right, a loop to the left. But the loop is part of a field, of a say, classical field configuration to the right. And then a field configuration, a contour, an embedding to the left. Hence it knows how to continue to the interior of the phase. What does it mean? It means that there is a momentum field on the loop to the right and to the left. But if I have a loop and momentum, I have a state in the phase to the right, and I have a state in the phase to the left. In this way, and I cannot have any state because the defect imposes conditions. If you just perform the standard, apply the principle of least action, you get the Euler-Lagrange equations in the phases as before, but you also get a defect gluing condition, which tells you what the kinetic momentum transfer at the defect is. And there is a non-trivial kinetic momentum transfer set by the curvature of the defect. And so not any two states will be set in correspondence, but only these described by this equation. In the space in which you have xi pi, this is xi, x1 p1, x2 p2, only those pairs which satisfy this equation will be matched. And you have a state correspondence on either side of the defect. But this is kind of cheap and naive. So let us stick to this defect gluing condition of momentum transfer condition at the defect and try to make sense of it in terms of classical symplectic mechanics. So you can now take the phase for the phase of states for the phase to the left of the defect. Take the space of states to the right of the defect. Since they don't interact, because the two parts of the world sheet do not cross, and this is my notion of interaction here in this geometrodynamics, I can just take the product of these as the phase space of the composite model. Right? And now I equip it, as usual, in search for symplectomorphisms, I equip it with a minus sign combined symplectic form. So I take the symplectic form for this phase space, I take the symplectic form for that phase space. the symplectic form is derived in this Stulji-Gawęcki-Piotr-Sztyrba formalism, or the, just to make this point, Witten-Chernkowicz formalism, or many people discovered it afterwards, but never mind. And I'm trying to understand what this condition means, and it defines an isotropic. For this form, it defines an isotropic, which means I'm dealing with a local symplectomorphism. But I go one step farther, because I know that my phase spaces have over them prequantum bundles, which I obtain through transgression of the cohomological data of the respective jerks. And so, I look at the isotropic and see that the cohomological data of this very special one isomorphism, which I put over Q, which related the two pullback jerks, actually transgresses to an isomorphism of prequantum bundles over the isotropic. So mind you, I have a prequantizable symplectomorphism. That's much more, and indeed, it is much more than just a symplectomorphism. It's a lift to the Hilbert space, once I choose a polarization. And then you can impose a natural condition of Hamiltonian preservation at the defect, which translates into a movability of the defect within the world sheet, because the Hamiltonian is the generator of if you place the defect on an equitemporal slide, the Hamiltonian generates translations in the time direction. Okay, and then you can of course consider defect junctions between defects, and you won't be surprised if I just tell you. You just look at this picture, get crazy, and I tell you what the principle is. I mean, we still haven't used two isomorphisms. So when defect lines join, what I do is I have several limiting field configurations at the defect lines, and I'm putting the defect junctions, depending on the balance, how many defect lines join there, I'm putting it in yet another manifold on which there is a certain two isomorphism. And never mind what the structure of this two isomorphism is, but I'm really using the fully fledged structure of the two category of jerks on the by now stratified target space of the charged loop mechanics with defects. Okay, right. And then I could gauge this theory as we did with Gawęcki and Waldorf, and I could then do many things with it, but let me not, because this is already a technicality. You know how to gauge a theory, right? You look for an equivariant structure, and the way you get an equivariant structure of the jerk, for example, is by considering gauge symmetry defects. And then you have to intersect the gauge symmetry defects with those which already existed in your field theory, and the thing gets complicated. But conceptually, the idea is very simple. So instead of elaborating on this already conceptually solved idea, which if you want to do string theory, or if you want to do spin and scattering in quantum spin chains, whatever your walk of life, the walk of life is that you come from, I don't give a damn, really, honestly. You may have to entertain the idea of doing proper higher geometry if you're dealing with extended charge distributions which interact with the corresponding higher gauge fields. But now I want to change the perspective completely, and instead of playing with the topology of the charge distribution to which a higher gauge field would couple, instead I want to challenge our choice of the symmetry model. Because what was the symmetry model in our case? It was always a group acting on a set. Like there was the set of states in the field theory, there was the set of sections of some bundle, there was the set of connections in that bundle, and so on. So there was the typical fiber of the field bundle, blah, 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 blah. It was always a set with extra structure on which a group was acting. But what does it mean that a group is acting? It means that every group element knows how to act on every point in the manifold or the set. That's a mighty rigid imposition to let every group element act on every point in the manifold. Because I might have local groups acting, so local orbits, local symmetries. And so that the first thing that I could change or challenge is our choice of the model of symmetry. not a group. And I'm going to tell you why this is really inadequate. Stick to groups. But also, I could challenge the model of commutative geometry as the model. Right? I mean, all these geometries that I considered, like say F, were based on structure sheaves which these were topological spaces with commutative coordinates. And I could challenge it in so many ways. I could pass non-commutative geometry. Rest assured, higher gauge theory GERBs enter the picture, as shown by Fröhlich and Gawensky, later taken up by Fröhlich and Recknagel. And together with Recknagel, we actually show that the GERBs matter when you construct this so-called loop, emergent loop geometry of strings. But that I won't follow. I will not also follow neither will I follow the other direction in which we relinquish the idea of a commutative sheaf of functions on a manifold. Namely, I can make it mildly non-commutative, graded, set to graded. And that's a path towards supersymmetric sigma models. GERBs also exist there. This is another path that I shan't take. Instead, I will just challenge the symmetry model. So oidization is a melodic subject of the last part of my talk. So here's why you should actually not think about just groups. Imagine the following question. You have a lattice in R2, a tiling of R2. Make it very regular. Nothing depends on that. Make it regular, but keep the plane gradients. Again, all right? Keep it extended. And ask which of the Euclidean motions on the plane preserve the lattice. You'd come up with some discrete answer, a group. But now, look at it again, cut out a big but finite region, and ask the same question again. You're screwed, right? I mean, the entire group, almost, generically, will go away. The translations will go away automatically, all the elementary translations, because the tiling ends. And again, since you're supposed to act with the group on each element, the ones on the boundary cannot be acted upon because here it ends. So the translation group is gone. You lose the information, right, on the elementary cell. But also, generically, the rotations will go, because if you cut it irregular enough, it won't have the properties of the full lattice. So the group, where is it? But that, all tilings in Alhambra are finite. And we derive our intuition about what symmetry is, not from planes. I mean, we may fly there, and then we get the intuition on a flight back on a plane, but it's not about R2, right? It's about planes. So anyway, so the point is to have a model which is good for a finite geometry. And Alan Weinstein proposed a solution. Instead of thinking of a group acting on a manifold, form the following slightly redundant description. Take the set of the following triples. A point in the set on which you act, another and a group element previously, which sends point M1 to M2, but both have to lie in this set, whose symmetry is your model. Okay? And then you get the full picture of symmetry in a finite region. I mean, this star can be moved to that star, and it needn't move infinitely far. But this star and this star, they sort of form a symmetric pattern, so if I replace this star with that star, the pattern stays the same. And I encapsulate it in this set, not in the group, if it's a finite set. And then you note that this set comes with what I call tentatively S, the source map. So if I think of this guy as an arrow, it starts at M1, and I say M1. Then there's a target where the arrow ends. It stops at M2, so I call it M2, and M2 encapsulates the action of the group, but a local one. And then there is an arrow which does nothing to each point, is the identity. Okay? It starts at M and ends at E acting on M, and that's one of the axioms of the action that E does nothing. Lucky E. So anyway, and then every arrow can be inverted, right? I just exchange the two endpoints, and then I have to invert the group element acting. And then I can compose that. If I can get from this star to that star, and from that star to that star, I can simply go from this star to that star right away. And it shouldn't depend on how I get there, right? So let's abstract from this simplistic analysis, which, however, is still superior to a group model of symmetries, a notion. So the notion is that of a group point. So here I come. I have an object, I have a set of objects to be acted upon. What the type? I have an object of arrows, each of which starts somewhere and ends somewhere. But it's not like every arrow can start anywhere and end anywhere, like in the group. No, no, no. Every arrow starts at some point, at a specific point, and ends at a specific point. And then to objects, I can attach arrows which transform them not. So the identity arrows. These are the distinguished arrows. And then every arrow, if I want to model symmetry, every arrow should be inverted. And then furthermore, if it's about symmetries, if I go from one symmetric replacement to another, and then one further symmetric replacement, I should get the same picture as I should be able to compose symmetric replacements in an associated way. And altogether, this is a group point. So a small category with all arrows inverted. What are nice examples of group points? Well, if you just take the arrow set to be a group and the object set to be a point, then every arrow starts and ends at every point because there is only one point at which to end. And if you look at the definition, you're getting, I mean, this is a set actually. So if you look at the definition, the set of arrows naturally implies the structure of a group. Okay? Then if you take a set and then a set of pairs of points in that set, there is the very trivial but kind of canonical and model structure of a group point. Namely, to each pair of points in X, I associate mentally an arrow, which starts at the first point and then ends at the second. And if I have a composition of composable arrows, so the one to the right ends where the one to the left starts, it's clear what happens here. I have a pair which is like M1 to M2, M2 to M3, and I say this is M1 to M3. As simple as that. And you easily check that all the axioms are satisfied. And then you can combine point 1 and point 2 and reconstruct, although now not in disguise, Weinstein's action group. Because now I have a group and I have a set. And I say that the set on which the group acts is the set of objects. And then the source of, and now arrows are just pairs, an element in X and an element in the group. And now the source is that element in X. And the target is the action of that element in the group on that element in X. And in this way, I encode through those axioms the action of a group on a man, on a set. So in particular, arrow composition encodes multiplication in the group. And now, if I put all the axioms in the smooth category, that means if I insist that this be a manifold, this be a manifold, this be smooth, this be smooth, this be smooth, then in order to make sense of the fiber product, I better ensure that both S and T are surjective submersions, which I do ensure. Then this pullback exists in the smooth category, and I can compose arrows. So I will be talking about Lie group points. There are sort of more structured examples which I skip now, but they are of interest in the symplectic setting, for example, in the group theory setting. Let me skip them. Instead, let me deal with Lie group points and the way they encode action. In what sense are we modeling some kind of action on the object set? Well, first of all, let us act on the group point. So the group acts on itself, but does the group point act on itself? the arrow manifold, does it act on itself? Yes, but in a tricky way. Because you see, you can only attach an arrow to the whole fiber consisting of those arrows which start where the acting arrow ends. So on the, well, here is this example on the S fiber. And likewise, for left action, I can only attach an arrow to those arrows, and all of them, which end where the arrow starts. That's the left action, on T fibers. And since T is a surjective subversion, T inverse is a submanifold. So this is actually mapping submanifolds to submanifolds. And since I assumed the multiplication to be smooth, it's a smooth diffeomorphism of, because every arrow has an inverse, of one submanifold into another submanifold. All right? But then I also have an action on the base of the point, and that's simply by taking, so I have a point, I can act on it with an arrow which either starts at it or ends at it, and then I say that the point is sent to the other end of the arrow which I attach to. I have those actions. So in this sense, groupoids act on both their spaces of arrows, or manifolds of arrows, and their object manifolds. And this is the thing that I want to gauge, because I find it more adequate, more comprehensive as a symmetry model than groups acting on manifolds. Okay? So what would it mean to gauge? Well, what it meant to gauge in the previous setting, where I had the group acting on a manifold as a model, it meant passing from the original manifold to its orbit space. Do I have any such notion here? Like reducing the internal degrees of freedom of a field theory by the action of the group, right? Do we have a similar situation here? Yes, we do, because you see we have those arrows which start and end at a point, over a point. And then these are groups. You can always compose these arrows in an associative way, but actually you can also show that these are Lie groups in this smooth setting. These are Lie groups, and they act in a free and proper way on the corresponding fibers. S fibers, if they act from the right, T fibers, if they act from the left. So I can form quotients, and those quotients are what is called orbits of the groupoid action. So I can still descend to what is called the characteristic foliation of the groupoid, which is the set of orbits. And nearly never is it a smooth manifold. But did I care any more in the previous setting, where I was modeling M mod G? I had this homotopy model of M mod G, which was the universal associated bundle, which I was pulling back to my spacetime. So good. So now I still have to understand how groupoids act on manifolds. So let me do that. So you see, the action of groupoids is a little tricky, because not any arrow can act anywhere. I can come up with the notion of a map from the space on which the groupoid acts to the object manifold of the groupoid, so that I can attach to it, in a smooth way, an arrow which ends there, if I want to write. And that's what is happening. I'm just saying that there should be what is known as momentum of the action, which maps the space acted upon into the object manifold of the groupoid, and there on this fiber product, which is well defined because T is a surjective subversion, so it's smooth, I have an action. And an action should satisfy what you expect the action to satisfy. Well, first of all, if you imagine that you send a point in the manifold to a new point, but you have ensured that this point is sent by the momentum to where the arrow ends, you can attach a new arrow to it only if the momentum of the new point is the source of that arrow, which you have just attached. So there is a sanity, kind of a natural assumption that you put here, and then you can insist that this action is a sort of like a groupoid homomorphism, that the action, consecutive actions by two arrows, is the action of the product of the two arrows, and then that the identity acts not. So this is completely natural, and there are models of such groupoid models. And then you can starting moving in the physical direction. What did we have in the physical direction? We had action of the group, which was fiber-wise, free and proper and transitive in the fibers. That was the principal line. So here we stumble upon the construction of Mackenzie-Murdyke and Jun, which is that of a principal G bundle. And we're almost there, except we're not. It's a very limited construction, and I'll give you a better one that we worked out with Thomas Strobel just now. So, but let me first tell you what the principal groupoid bundle is. So it's a surjective submersion, and I couldn't emphasize it more. It won't even be a bundle. It's a surjective submersion whose total space is the right groupoid module, and the action along the object manifold of the groupoid on this total space is fiber-wise relative to the surjective submersion, and there it's free and transitive in the sense that for any 2 points in the fiber, in the same fiber, there is an only one arrow which sends me from one to the other. Okay, this is science. So then, if you work on it a little bit like Murdyke did, then you realize that it's not a bundle in a very special way. Namely, if you use local sections of this surjective submersion and pull back the momentum map to the object manifold of the groupoid, then you get directly smooth maps from the base of the surjective submersion to the object manifold, and you then see that locally the surjective submersion looks like a fibration by T fibers of the images of points that you get by those local. So the T fibers vary dramatically from point to point, and that's what you're getting. It's not a bundle. It's not a bundle. Okay? Excellent. So, right. So now we want to gauge groupoidal symmetry, and we know what we're talking about. All right? So in order to even start the construction, and the construction will start before, so stop before long, come to an end, and a happy end at that. Let me walk a few steps back and ask the question, so how did we get, can we see somehow the groupoid in the standard construction of gauge transformation? Well, where did we get the gauge transformations from? We had this extended principal G bundle on which the action of the group was fiber-wise, free and proper, so we could form the quotient, which was the associated bundle. And the point was that gauge transformations were those automorphisms of the bundle P times F, which were surviving the quotient. And they were coming from automorphisms of P, because we wanted them to be modeled on left action of locally smooth profiles in the group on trivializations of P, on fiber of P. So let's try to understand it now in groupoidal terms. What's the fiber of P times F? Well, it's G times F. What's the fiber of the associated bundle? Well, it's F. But as it happens, G times F and F, they compose the arrow manifold and the object manifold of the action group. Good. So let us now try to understand this passage, this quotient map, as a statement about the existence of a structure of a principal action groupoid bundle on P times F. And then we will see that the associated bundle is basically the quotient of P times F by the action of the groupoid, which is free and transitive. So let's do that. I have a simple choice of the momentum map of P times F. It's just projection to the second factor. And then I know what the action is. So let me first see what the action looks like. The action that I'm quotienting by in order to get from here to here. So I should add that. What I want to model in groupoidal terms is the passage from P times F to the associated bundle. I view it as a quotient by the groupoid action, right groupoid action. So here it is. In local trivialization, so here, I have a pair, an element in the group and an element in F, and there is an element in the group acting like so. I told you that I'm quotienting out this diagonal action. So I want to manipulate it so that it looks like groupoid multiplication. So I can do it trivially. This is the arrow in the arrow manifold of my groupoid, the original one. And this is another arrow, which when I compose the two, I get the arrow I want. But this is still not good enough, because you see, this arrow knows about the point on which it is acting. Not good. I mean, I cannot fight it. It will be an arrow, so it will have to end where the other one starts. but I want to construct a smooth function from F to the arrow manifold, which when evaluated at the starting point of this arrow will produce that arrow. The benefit will be that this will be a function which will know how to act on the entire arrow. And that's where I'm heading. And this is the arrow. Okay, so how it is constructed. There exists an arrow like that. Okay, so S of GF is just F, H inverse F. If I invert it, I get this guy. And now, so I have the action that I'm quotienting out in groupoidal terms. Now I want to describe the gauging action, which descends from here to here, which survives this right action. It commutes with it. It's equivalent. So here it is. It's locally modeled on the left, on the action from the left on G by smooth profiles in G. So again, I play the same silly game, and I see that I'm getting an arrow on the left. Again, a function on the object manifold evaluated at the target of the arrow acted upon. And now I make an abstraction. So the abstraction is the group of bisections. You see, the global thing to think of how groupoids act is bisections. So bisections are sections of the surjective submersion, global ones, given by the source map, such that if you, so what does it mean that it's a section? So if I have this mapping from the object manifold to the arrow manifold, and if I post-compose it with S, I regain the original point in M. But if I post-compose it with T, all over, I get a diffeomorphic transformation, auto-diffeomorphic transformation of M. This is what groupoids sort of encode globally. These are the groupoidal transformation, the group of bisections. So you can convince yourself that this is actually a group. There is a setting in which the group multiplication is even smooth. It's an infinite dimensional. Come on, we're talking about smooth maps. There are quite a few of them, and you compose them, so it can only be smooth in this convenient setting or the theological setting or whatnot. I shall not go there. But anyway, you might think, well, yeah, yet another mathematical object. Who cares, right? I mean, how many objects can you have? Many, right? For everyone's pleasure and sort of, yeah, perversive pleasure. But these are maybe a little perverse, but useful too. And perversity, which is useful, is the best perversity I can think of. So here's the usefulness, and I leave you with this message. So anyway, so what about bisections of this groupoid over a point? It's just a group. Okay, good enough already. It's not like a point. The bisections of the pair group. Here it already gets a bit interesting because we have a full diffeomorphism group of M. So if we gauge it, pretty far, right? I mean that, and between these two extremes, or actually I could take the groupoid M over M trivially, and then there would be just one bisection, right? Not doing nothing. So between nothing and the full diffeomorphism group, that's quite a lot to gauge, quite a lot of possibilities to gauge. And indeed, if I take the bisections of the action groupoid, there is a subgroup of those very special bisections that I considered, which is diffeomorphic to the group. And then I have actions of bisections on the arrow manifold, defined very simply. Action from the left, action from the right, adjoint, I will be using these. And then I have the so-called shadow action on M. What is the shadow action? If I have M, I can map it by the bisection to the arrow manifold, and then I can post-compose it with T, and it's a diffeomorphism. So it's an action by diffeomorphism on the base of the group. And now the physics, the gauge. So let me reproduce this logical scheme in which we have P times F surjectively submerging by the quotient map P times lambda. So our associated bundle whose sections would be our fields in a field theory with the symmetric gauge in this setting. So what was P times F? It was a bundle with a typical fiber given by the groupoid. And the gluing was, when you come to think of it, by the action of those arrows, which only act on G. There was the fiber G times F, and I was just gluing by the transition mappings of P. So here I would be using the left action of a cocycle with values in the bisection group. Okay, I fix the cocycle. I use the clutching theorem. I'm talking bundles. So a bundle is just the cocycle. And then I have to specify how I glue the local models by the cocycle. Here how I glue it, by the left action of the bisection group on the typical fiber. Then you can get a little fancier and less cumbersome with all the indices and say that actually you get this structure as a model, but if you insist that the principaloid G bundle, which is how we called it with Thomas, is the right B space in the category of fiber bundles with typical fiber G and the B action locally modeled on R. And it turns out that you get this. It's not entirely trivial because you have to find the commutant in the diffeomorphisms of the right action by the diffeomorphisms of the arrow. But now I can replay the logical scheme that led me here. The construction of gauge transformation. Because I have P and I have a morphism of bundles locally modeled on. So I have a bundle with a typical fiber. What else? This was the associated bundle. And a morphism of bundles locally modeled on the target map, which enables me to think of P as the right Lie groupoid module for the momentum map, which is locally modeled in P, locally modeled on S here, and and an action which is locally modeled on the right action of the Lie groupoid on itself, and that all that fiber is over sigma. So hence this, I could sort of say that it's a principal G bundle object in the category of bundles over sigma. Maybe wouldn't tell much. But now I have the statement that since this action is principal, I can think of F invariantly as the quotient of the principaloid bundle by the groupoid action, which is canonical there. And then I have examples. So if I take this groupoid G over point, I get the standard principal bundles. If I take the pair groupoid, I get generic bundles, Michos bundles, because I have the full diffeomorphism group unconstrained as the structure of the bundle. And then if I have the action groupoid and very special bisections to glue it, then I get reconstruct my thing. P times, well, previously it was P times F over the associated bundle. So I have attained my goal. And then there is a story about connections. So on every principaloid bundle, I have a compatible connection, meaning an Ehresmann connection. Let's not discuss sort of completeness, but it is also kind of discussed there. So it is right bisection invariant. I choose Ehresmann connection with a right bisection invariant, and these I can represent as one forms on the total space of the principaloid bundle with values in the vertical subbundle, which is, since I'm doing bundles, which is always well defined as the kernel subbundle, kernel with respect to the tangent of the projection to the base. And then I impose the extra condition of right invariance. And in order to tell you what this looks like locally, and that will be the last slide, I have to introduce to you the tangently algebroid of a Lie groupoid, because I want to present you with the notion of a foliated one form on, let's say, one form on the base of the bundle with values in an object which is to the Lie groupoid, our gauge symmetry model, in a relation in an analogous relation as the Lie algebra, in which a principal collection one form takes values in the local presentation, to a Lie group, which was our symmetry model previously. So what is the Lie algebroid? It's a vector bundle over some space, over some manifolds, with a mapping to a vector bundle which can canonically be associated with that space, namely the tangent bundle, such that I have a Lie bracket on the space of sections of this vector bundle, and this Lie bracket, owing to the existence of this anchor map, of this vector bundle morphism, can be consistently made into a sort of derivation module derivation on the derivation of the module structure or on the space of global section of the vector bundle E. What is the module structure? If you have a vector bundle, you can multiply pointwise every smooth, globally smooth section by a smooth function on the base. And I should be able to differentiate this module structure, and that's the Leibniz property of the bracket, which I phrase in terms of this bundle map. As it happens, as a result of this axiomatics, alpha is also a homomorphism of Lie algebras, spaces of sections. Okay, so I have some obvious examples, but let me not go there. Let me construct the Lie algebroid for you for a given Lie groupoid, which is the symmetry model for our symmetries to be gauged. So, a word of caution. Just quickly rewind the tape in your head and think how you construct the Lie algebra. You look at right or left invariant vector fields on the group. Let's look at right invariant vector fields on the Lie groupoid. But here we have a problem because the right multiplication is fiber-wise. It sends S fibers to S fibers. So in order to even define right invariant vector field, I have to look at vector fields which are tangent to S fibers. Only those. And then if I have them, I know that the right invariant vector field will be fully defined by the intersection of the S fiber, and it's always transverse, the intersection with the identity bisection. So M, the object manifold, maps into the arrow manifold as the identity bisection, the identity arrow here. And S fibers transversely through. So since I have right invariance, I should be able to define the right invariant vector field by restricting it to the identity bisection. And then there is a natural bracket on such objects, which you use in the standard Lie group type way. So I will not go through the details. We have the Lie algebroid, which is just basically the pullback by the identity of this subbundle curve ES. It's a subbundle due to the constant rank theorem for vector bundles. S is a surjective submersion, so S is the constant rank map and between bundles. TS is a constant rank map between bundles because it's a submersion, S is a submersion, and so I have a subbundle. And now I will gauge fields in my theory. These are actually sort of, well, they're forms on, and this is a caveat, these are forms on a piece of the space-time over which I have my gauge bundle times the object manifold of the groupoid with values in the Lie algebra. Okay, these are the guys. I can work out the transformation properties of these guys, and also I can push a la Kobayashi no Mizu. I can push the overarching principal Ehresmann connection on the principaloid bundle all the way down to the shadow bundle by the sitting dot map, so this map D, which I introduced previously, very previously, even more previously, here, this one. So then I get a connection on, if you will, some sort of associated bundle, on the matter bundle. And now, I can say what automorphisms of P are, my gauge transformations. I will model them locally on smooth profiles in the bisection group. From these, I can push them down to the shadow bundle, using essentially this sitting dot map, this D between bundles. So I get gauge transformations on the matter bundle, induced from automorphisms of the principaloid bundle. And okay, this is encoded by a certain Atiyah groupoid, and it's a bit tricky. This is math. Everyone should care, but let's not at the moment. Let me just finish by saying that the coupling, which I at the very first moment of my first lecture, I told you that there are many ways to think about gauge theory. Let me think of the gauge theory here. The coupling of the gauge field, which now is the gauge field for groupoidal symmetries, to the charged matter field, so the second geometrization of a current, is by the covariant derivative, in the case of tensorial couplings. And Kubat-Liebig is working on non-tensorial couplings in this setting. Groupoid equivariant structure. If you know, and you should know what I'm talking about. So this is the equivariant structure, and the equivariant structure is just this. You take this projector obtained by pushing down the connection 1 form from the principaloid bundle to the matter. And you use this projector on the tangents of a section of the matter bundle, and this is how we obtain a covariant derivative, and this is how we obtain minimal coupling of the gauge field, which sits here, to the matter field, to the charged matter field. So, okay, I'm done. I hope to have convinced you, or at least whetted your appetite, as concerns the structure of higher gauge theory. Already, and I wanted it to be like that. When you consider some such mundane thing as a charged point-like probe moving in an external field, but start playing with the topology of the space-time in which you get high. You get those higher geometries which geometrize the gauge field. Then you may start using this construction, the abstraction of this construction, to gauge a symmetry of this. Next, you may start playing with the topology of the charge distribution, and you get even higher because you get those gerbs and whatnot. And then you may replay the story and gauge a symmetry in the presence of the gerb, which means equivariantization. But finally, okay, non-finally, penultimately, you can start playing with the commutativity. You can challenge the model of space-time, and the space is involved, and consider non-commutative geometry. Gerbs play a role there in the string theoretic context. You may start making the spaces Z2 graded. That's supersymmetric string theory for you. And you have supersymmetric gerbs. Quite nice. And then finally, you may challenge the model of symmetry. Relinquish the highly inadequate model of a group acting on a manifold and pass to group points. And so I hope that you sort of, along your further way, you find this useful or at least inspiring. Okay? Yeah. So thank you very much.